Hello and welcome to the OpenRelay Screenside Chats Episode 3. Today we are going to be talking about our affiliate program. So I've selected the affiliate program because I think it's a great case study for exploring OpenRelay. It'll give us an opportunity to talk about smart contracts. It'll give us the opportunity to show a Web3 dApp in action. And we'll also be able to explore a small microservice. The neat thing in my mind about the affiliate program is it gives us a good breadth of categories on several fairly simple components so that we can cover the implementation of each without losing sight of the big picture to kind of help cover each of the individual concepts. So we're going to start with an architectural overview of the affiliate program. So suppose you got a developer who wants to make a dApp, and they want to integrate with OpenRelay. The developer can go to the affiliate contract on the blockchain, and they can sign up for an affiliate account. The affiliate factory contract will create a smart contract specifically for that developer. And that affiliate contract will define a predefined fee split between that affiliate and OpenRelay. This split cannot be changed once the contract has been defined. So once that contract is created, whatever fee split it was created with is going to be permanent. Out of the gate, we're looking at an 80-20 fee split where the developer will get 80% of the fees and OpenRelay will take 20% of the fees. That could change at some point in the future, and through the affiliate factory contract, we have given ourselves the ability to change that for future contracts, but any contracts that are made at a particular point in time will be set at that fee split in perpetuity. As the smart contract, the affiliate factory smart contract deploys the affiliate contract, it will also emit an event. And within the OpenRelay set of microservices, we have a monitoring service that is watching for these events. And when it sees one of those events, it writes that affiliate's contract address into Redis so that subsequently we can accept orders that come from that affiliate. So once the developer has their smart contract, they take the address of their affiliate contract and they embed it into their dApp. They deploy their dApp. They handle marketing, building whatever assets they want their users to be trading, and they bring users to their dApp. When a user comes to their dApp and creates an order through the dApp will upload it to OpenRelay through our ingest service. The ingest service will go to Redis to see whether this fee recipient address on the order corresponds to an affiliate recognized in the Redis database. And if it does, it will get approved. If it doesn't, it will immediately reject the order. Then it sends the order. If it gets approved, it sends the order off to the validation pipeline, and it eventually makes its way into our database. Later on, another user, possibly using a different dApp, can search our order book. When they find an order that they're interested in filling, the dApp will submit it to the 0x exchange contract on the user's behalf. The 0x exchange contract will take care of swapping tokens from one user to the other, and it will also take a fee from each of them. It takes that fee and it sends the fee to the developer's affiliate contract. Once it's there in the developer's affiliate contract, it can be dispersed both to the developer and to OpenRelay. The neat thing here is that the fees go directly from the 0x exchange contract to the affiliate contract, and OpenRelay never holds the developer's fees. We're not paying the affiliates. The smart contract, the affiliate smart contract is paying the affiliates, and it's paying us. We never have the opportunity to interfere with this process. We could potentially stop accepting orders from a particular affiliate if they broke our terms of service. But once there are fees in this smart contract, those fees are going to be dispersed 80% to the developer and 20% to us, and there's nothing we can do to change that. So here's the big picture where you can see all of the pieces connected to each other. Again, we have our affiliate contract. Next week, we will look at our affiliate sign-up DApp, which is a fairly simple DApp that allows you to sign up through the affiliate factory. And then we will also be taking a look at our monitoring service over here as an example of what our Go microservices look like. So that's it for the architectural overview. Do you guys have any questions about the architectural overview before I start looking at the contracts that are actually written in Solidity?
Maybe you said this, but I might have missed it. With since this is a shared order book that OpenRelay is facilitating for 2 different, possibly 3 or multiple different affiliates to have on their that they're displaying to their customers, how does OpenRelay handle the fee structure between a order submitted from one DApp to an order from another DApp whenever they have maybe different
Right. So I think your question is, how do we handle when the maker of an order comes from a different DApp as the taker of the order?
Yes, along with the fee structure involved in that process.
So in 0x version 1, there's not a whole lot we can do on chain to deal with that scenario. So if the taker comes, or if the maker provides a fee recipient, that is the fee recipient that gets paid. There is nothing we can do as an automated part of this process to pay the taker. That may change with 0xv2 through the Cinder capability. There are some things that we're exploring that may give us the ability to do a fee split that also includes the taker DApp. But the other thing on that front is we actually don't have much trouble finding people to take our orders. Even now, if somebody uploads an order to OpenRelay and it's reasonably priced, it will get filled. There are a number of services that are pulling our order book and making them available to their users, and we're not having to offer any incentive for them to do so. The main thing that we're particularly interested in offering incentives for is people who can bring us liquidity, which are going to be on the maker side. At some point, we may explore options for offering incentives for people on the taker side as well. But yeah, our initial incentives are really structured at people on the maker side of the equation. Does that answer your question?
So affiliate is on maker side only currently then?
That is correct.
Okay. Austin, so you would say the goal of the affiliate program is to make it so that developers can pick up OpenRelay more easily.
Well, yeah, but we want people to be able to pick up OpenRelay more easily. But if you have a DApp that is only going to pull liquidity right now, we have no way to incentivize you. The only way we have to incentivize you is if you are the one bringing us liquidity. Again, that may change at some point in the future. These are the constraints of 0xv1, but we are exploring how we might be able to offer taker liquidity in 0xv2.
Cool stuff, man.
All right, so first we are going to take a look at the affiliate contract. Later we will look at the affiliate factory contract. So first of all, this is some boilerplate that you would find at the top of our affiliate contract. So the pragma at the beginning says that we're using Solidity version 0.4.18 or higher. practically speaking, if this were something that we were going to rebuild a bunch of times, we would probably want to pin that to a very specific Solidity version. I would also note that that does not mean that when you go to compile, it will compile with that specific version. What that means is if you are trying to compile with a version of the Solidity compiler that is not that specific version, it will just crash and tell you you need that specific version. Moving past that, we have several import statements. So the first two imports come from the OpenZeppelin project. OpenZeppelin is a great resource for contract building blocks. So the first piece that they have there is the safemath.sol. The safemath library tells you how to do, or helps you do arithmetic with unsigned 256-bit integers. So the problem that you can run into using unsigned integers is that if you exceed the size of that integer, you overflow and you end up with a smaller number. So like using an 8-bit integer as an example, the biggest 8-bit unsigned integer is 255. So if you did 255 plus 1, you'd end up back at 0. The numbers are much larger with 256-bit integers, but you still have the same problem, that if you added the largest possible integer to itself, you would end up with some number smaller than that. So the SafeMath library gives you a bunch of tools for doing math in a way that you're not going to run into those problems. The next piece here is the ERC20 library. So ERC20 is the token standard that we are supporting with our affiliate contract. And basically, we're using this as an interface. So we will deal with a variety of different ERC20 contracts. But the important piece is that they implement this ERC20 interface, and we can call some standard functions like transfer and getting balances. The next import that we have is WEAth9. So WEAth stands for Wrapped Ether. I'm not sure actually what the 9 comes from, but this is a very standard contract. It's used by MakerDAO. It's used by the 0x project. Basically, it is an ERC20 token that wraps Ether. So you can deposit Ether into the WEAth9 contract and then pass it around as an ERC20 token, taking advantage of some of the features that ERC20 tokens have that Ether itself does not. And then you can unwrap your Ether later, all through the WEAth9 contract. Finally, we have the registry interface. So this is something that we have defined internally. It is not something that is coming from an external source, but basically we have an affiliate registry, and we want to be able to check whether or not a given user is affiliated. So we're saying that there's an interface that some contract that we relate to will offer this is affiliated signature and return true if the address passed into it is an affiliate, and false if the address we pass into it is not an affiliate. Next, we get into our contract data. So we have our affiliate contract defined up at the top. And for what it's worth, these slides are essentially sequential moving through the code. But I didn't want to put it all on one slide and scroll through it because that would be harder to follow. So within our affiliate contract, we define something called a share. And so a struct is similar to a class if you're familiar with class-based programming in something like Python or Java. But a struct is a little bit more limited. I don't know if you can attach methods to a struct. You can't subclass them. They're not as robust as a class, but they allow you to group certain pieces of information together. In this case, for each share, we want to group together the address that corresponds to that share's shareholder, and an integer, an unsigned integer, indicating that particular user's stake. The stake is basically what is their share of this overall affiliate contract. So then after we've defined our share struct, we declare a shares array an array that is a global variable within our contract. So when we write something into this shares array, it gets stored in the Ethereum state tree and can be accessed by a subsequent transaction. And that's true for all of the global variables that we're looking at here. So shares is going to be a list of the shares that we just defined a struct of earlier. Then we have our total shares integer. So this is public information. Anybody can look and see how many total shares there are in this affiliate contract. Then there's a public string called relayer name. I'm kind of trying to establish a pattern here that I'm hoping other relayers that use contracts as the fee recipient may follow. But basically, since we will be deploying a bunch of different affiliate contracts, and there's services like zeroxtracker.com that when they see an order get filled with a particular fee recipient, they want to name the relayer that address corresponds to. With this, they could simply go to that address, see, okay, it's a contract, it implements this relayer name function, call that function, and get the relayer name so they can list it on their site. Then we have an address for a registry. This corresponds to the registry interface that we were looking at before. So this is the address that they're going to be able to use to determine whether or not a given address is affiliated with this contract. And the idea there is that OpenRelay has multiple affiliates, and this kind of gets back to our taker fee sharing process, that if the fee recipient is affiliated with some other address, that we'll have to figure out some way to incorporate it, and that is also an affiliate, that we will allow the fee split to split in multiple directions. Again, there's a lot that we haven't figured out there, but I'm kind of leaving myself some wiggle room, and the affiliate contracts that we deploy today can tell if they are affiliated with each other. Then we have an instance of the WETH9 contract that we're calling WETH. This is what we will use to deposit and withdraw Ether should somebody pay this contract in Ether. Finally, we have a payout event. So when somebody calls the payout method to distribute the fees to the various affiliates, that will emit a payout event that can be monitored on the blockchain. Then we get into the initialization function. And note that this is not the same thing as a constructor. Most Ethereum contracts have a constructor that is called at the time that the contract is deployed. The way we are doing the affiliate contract system, we are actually using a proxy model, which I will get into when we get into the affiliate factory. But basically, we can't do this through a constructor, so we provide a different initialization function that we have to call the first time, or as soon as we have deployed a proxy for the affiliate contract. So this initialization function takes a registry address so that we know where our registry is. It takes a list of shareholder addresses. So in the diagram I had earlier, we showed one developer as the shareholder, but we could actually have multiple shareholders beyond just the developer and OpenRelay. We can have essentially as many as we want. We also pass in a list of stakes. You'll see down here that the list of shareholders has to correspond to the list of, or it has to be the same length as the list of stakes. With newer versions of Solidity that haven't quite been finalized, it's possible to pass in a list of shares. So we have our share struct that we looked at a few slides ago. In newer versions of Solidity, we can actually pass in a list of shares. But in this version of Solidity, we can only pass in standard data types like addresses and integers and lists thereof. So so we couldn't pass in a struct that we defined as a parameter to this function, at least not for public functions. We pass in the address for WEATH, and we pass in the name. This is a public function. That means anybody can call it, including this contract can call itself. And this function is going to return a Boolean value. So looking in here, we require that the total number of shares is equal to 0. That means that you can't call the initialization function after it has already been called, because the total shares will have been increased past 0. So that prevents somebody from coming in here and changing the share allotment after the fact. Again, we make sure that the shareholders' length is equal to the stakes length, because those are two sides of the same coin. We keep track of our WEATH9 contract. So this is going to be, again, where if somebody pays us in Ether, we are going to deposit that into the WEATH9 contract so that we have ERC20 tokens instead of Ether. Here, and I noticed this as I was preparing the presentation, we set the total shares to 0 before we loop over and increment it. We had just validated that the total shares was already 0, so it's very implausible that it would be anything but 0. But I guess this is kind of a belt and suspenders, and maybe I wasn't paying attention when I wrote that. So as the next point, we iterate over the list of shareholders. And in our shares list, so this is our global list of shares that we keep track of, we construct a share providing this shareholder out of the list and this stake out of the list. So it's mapping the shareholder in a given position to the stake in a given position, constructing a share object and keeping track of those things together. Then we increment the total number of shares by the number of stakes that this particular shareholder got. So ultimately, it's not going to matter what the total number of shares is. It's not like it always has to be 100 or it always has to be 1,000 or anything like that. However many shares we get, and then we will divide things up evenly when we do a payout. Finally, we keep track of the relayer name in the registry, and then we return true to indicate that we succeeded. If either of these require statements up here failed, then we are going to throw a revert, which is going to undo anything in the transaction that had been done up to here. So practically speaking, this contract can't return, or this function can't return anything but true. But we're, again, kind of belt and suspenders, just returning true, and we will validate that in the affiliate factory contract to make sure that it did return true and nothing went haywire. The other factor is our affiliate factory contract allows us to change the affiliate contract for new affiliates, and at some point in the future we may have a condition where we may return false or we may return true. So having it return true and validating that gives us a little bit more flexibility for future growth of affiliate contracts. So next we have our payout method. And as the comment notes, we're going to, when somebody calls the payout function, they pass in a list of tokens. And we are going to pay out the entire balance for every one of those tokens to all of the shareholders every time that this payout function gets called. Early on, I entertained this idea that we would try and keep track of who has withdrawn their tokens and who hasn't, and every individual will be responsible for withdrawing their own tokens, but that created a complicated bookkeeping mess. So instead, I decided when we do a payout, we're going to take the balance of the token that we're paying out, and we're going to pay it out in its entirety to the recipients, so that once we're done, the balance will be within a rounding error of 0, and there will be nothing left to keep track of in terms of who still needs to get paid. So we've passed in a list of token addresses. We're going to iterate over that, and we're going to construct an ERC20 object corresponding to the address that was just passed in. We get the balance of that token for this contract. So that is, what is the affiliate contract's balance of that token? And then for each shareholder, we are going to iterate over the shareholders and transfer that token from ourselves, that's implied by calling the transfer function, to that shareholder. And the amount we are going to transfer is our current balance multiplied by that shareholder's stake divided by the total number of shares. So that is, if there is one share and this shareholder has it, they're going to get whatever the current balance is. If there are 100 shares and this shareholder has 50, then they are going to get the balance times 50 divided by 100. So they're going to get half the balance. And for however many shareholders we have, they can have different stake allocations. Doesn't matter. They get their stake of our current balance of this particular token. There is the possibility of a rounding error, but because of the way we're doing this, we always round down. So any tokens that don't get paid out will just stay in the contract to be paid out the next time somebody calls payout. And then finally, we emit a okay. So that's going to iterate for every shareholder for every token and pay out all of the tokens that were passed in this list to all of the shareholders that belong to this contract. And then for each token that we pay out, we indicate the token, we emit an event indicating the token that was just paid out and the balance of that token. So how much we just paid out. And that is so that off-chain systems can follow along and keep track of when they got paid if that's something that they're interested in. Finally, we have our fallback method. So I mentioned earlier that if we get paid in Ether, then we're going to keep track of that as WETH. Ethereum contracts, in order to get, if you just send Ether to an Ethereum contract, if it does not implement what's called a fallback function, and that is a function that has no name, you'll see that this function doesn't have a name. If it does not implement a fallback function, and the contract gets paid, it will revert that transaction. So it will reject any payment of Ether that it receives. Now, the current model for our affiliate program doesn't have anything to do with Ether, but future variations of our affiliate program may involve people getting paid in Ether. And that aside, if somebody wants to send us Ether and we can split it between OpenRelay and the affiliates, and we're happy to take their money. At least this way, it doesn't get locked away somewhere where it will never be retrievable. So when this fallback method gets executed, that means that somebody has just paid Ether to this contract. We're going to make a deposit in the WETH contract with the value of however much Ether they've just sent us. That means that we will end up with an ERC20 token corresponding to that value, and that ERC20 token can be paid out through our payout function, just like everything else. There's a number of reasons that it's preferable to do that payout method with ERC20 tokens, not the least of which is that way we don't have to have one payout function for tokens and one payout function for Ether. It simplifies things. There's also some security parameters dealing with reentrancy and some other stuff that make it easier if we know we're always paying out an ERC20 token and that none of the people that we're paying out to are contracts that are going to have their own fallback method, which may cause problems as we try to send them Ether. So just sending tokens should always work. And so keeping track of any Ether we get paid as wrapped Ether tokens makes things a little bit simpler. Oh, and lastly, we have our is affiliated method. So if we have an address and we want to know if this address is in the same affiliate network as this affiliate, we can pass this affiliate an address that will go to the registry to ask if this affiliate is in the same affiliate network and return true if they are and false if they aren't. Does anybody have any questions about the affiliate contract before I move on to the affiliate factory contract? Because if you didn't get this, the affiliate factory contract is quite a bit more complicated. Questions? No questions?
So far, so good for me.
That makes sense.
Sorry, Sam?
I had a few questions, but I read your comments in your code, and you already covered them.
Okay. All right, so now we're going to talk about the affiliate factory contract. This is where affiliates come to sign up for their own affiliate contract. This is also written in Solidity. The vast majority of Ethereum contracts are written in Solidity. There's a new language that's come out called Viper that people are starting to write contracts in. It's a simpler language, doesn't have things like contract inheritance, makes things a little bit easier to formally validate. But in any case, our affiliate contracts are all written in Solidity. Again, we have some boilerplate. Our Solidity Pragma, we're importing SafeMath and the affiliate contract that we were just looking at. The other thing that I want to note here is that we are importing the ownable contract from OpenZeppelin. So the affiliate contract is ownable. That means there is an Ethereum account that is able to execute particular actions that nobody else is allowed to execute. And we will look at some of those as we go. But basically, this is a standard implementation of the concept of an ownable contract. With it comes some standard capabilities like reassigning ownership. Only the owner can assign ownership to other people. It also has, I can't remember what they call it in Solidity, but it's comparable to the Python concept of a decorator that allows you to say that a particular function can only be called by the owner. So here we can see that we applied the ownable interface to the affiliate contract by saying that the affiliate factory is ownable, which makes a reference back up here to this thing that we imported. So again, we have contract data. This time we have an affiliate deployed event, which is a bit more complicated than the payout event. Basically, it describes the affiliate address, which is the contract address of the affiliate that we just deployed. The target address, which is the affiliate contract that the proxy we're deploying is pointed to. We have an affiliate name, which again is if somebody wants to know what is the name of this affiliate, or what is the name corresponding to this fee recipient address, they can go look at the affiliate name. They can also, I mentioned 0xtracker.com earlier. If they wanted to, instead of looking up an affiliate at runtime when they've just seen a fee recipient contract come through, they could monitor our affiliate deployed events and keep that in their database on a proactive basis. So as soon as an affiliate gets registered, the event gets emitted, provides the affiliate address and the affiliate name. They put that into their database, and then they can report it as soon as the first thing comes through without having to do anything once they've seen an order. Finally, we have the sender of this affiliate deployed, or of this sign-up event. And the important thing about the sender, and the only reason we have that there, is to give the person who just signed up an easy way to monitor for an event that shows them that their sign up is completed. So they would not know the affiliate address in advance. They wouldn't necessarily care about the target address, plus everything else is going to be using the same target address. And if somebody wanted to be a jerk, they could deploy another contract with the same affiliate name. So the sender is the easy thing for them to track so that they can know when their contract has been deployed. Then we have several additional public variables. We have a target address. So this is when we deploy a new affiliate contract, it is going to be a proxy for this target. What that means is whatever this target contract, whatever code is at this target address, that is the code that is going to get executed by the affiliates. So we have the beneficiary. That is who other than the person signing up gets a stake in the affiliate contracts that get generated here. So in this case, OpenRelay is going to be the beneficiary. We are the ones who get paid when affiliates do payouts, aside from the affiliates themselves. We also need to keep track of the WETH contract. We're not keeping... The affiliate factory doesn't directly interact with the WETH contract, but when it initializes an affiliate contract, it needs to be able to provide that address. Then we have an integer for the beneficiary stake, and we have an integer for the sender stake. So the beneficiary is what is OpenRelay's stake. The sender stake is when somebody signs up, what is their stake going to be? So right now, that's an 80-20 split. In practice, when we deploy it out to mainnet, that's going to be 8,000 shares for the sender stake and 2,000 shares for the beneficiary stake. Originally, I had thought we'll just do 80-20, but doing 8,000 and 2,000 gives us a little bit more granularity in terms of percentages, so we can deal with more affiliates signing up and getting a more precise breakdown of each person's shares. Finally, we have a mapping of Ethereum addresses to strings. So this is going to be what is the name of this affiliate. So when they sign up, they provide us with a name. We're going to keep track of them, that in this mapping, in addition to keeping track of it on their specific contract. So this contract, unlike the affiliate contract, does have a constructor. This is a function that executes at the time that the contract gets deployed. We can see that it takes a target address, WETH address, beneficiary stake, and sender stake. We just talked about what all of those things were, so I'm not going to go into it again. This is a public function because constructors have to be public, even though they are only executable at the time that the contract gets deployed. We also call the ownable contracts constructor as a part of this, and that will set up whoever deployed this contract as the initial owner, and do some other bookkeeping. Then from there, the constructor just calls update. So the update function down here will be callable only by the owner. So this is, again, the Solidity version of a decorator saying that only the owner is allowed to call this function, and it will defer that to the ownable part of the contract that is not implemented in this file but comes from OpenZeppelin. So in the future, the owner can call the update function to set a new target address, a new beneficiary, the WETH address, the beneficiary stake, and the sender stake. You'll note that the constructor did not take a beneficiary address. That just defaults to the sender of the message. So whoever set up the contract becomes the initial beneficiary, but that can be changed through the update function. And then all the update function does is it takes the parameters that are passed into it and it saves them off into the permanent storage variables. So administrators can register affiliate contracts with less constraints than somebody who just wants to sign up. So only the owner, so that's OpenRelay, can call this function to set up a contract with a certain number of stakeholders, corresponding shares for each of those stakeholders, and giving it a name. If we call this function, we don't necessarily have to be a part of it. So we could potentially grant somebody a 90-10 split or a 100% split, or a 50-50 split for two parties that aren't us. That is left to our discretion, so we can register affiliates that get special deals. Then this is an external function, which means this contract cannot call that on itself. It can only call it, this function can only be called from outside the contract. Only the owner can call it, and it returns an address called affiliate contract. You'll note we don't actually have to return affiliate contract down here in the function because we have declared this variable up here and said we are going to return it. All we have to do is set the variable, and it will automatically get returned by this function. So we are going to get the affiliate contract address by calling create proxy implementation, and we pass in the target address to be the target of the proxy. We will look at the create proxy implementation function in a few minutes. It's mind-numbing, but really, really neat. Then we have, once we have deployed the affiliate contract, we turn it from an address into an instance of an affiliate contract. We call the init constructor to pass in this address. So this is the registry, the list of stakeholders that we just passed in, the list of shares, and the address of the WEATH contract and the name that we just passed in. We keep track of the name in our registry of who our affiliates are, and then we emit an affiliate deployed contract so that people can see that this just happened. This is the simple version, but only administrators are allowed to do it. When we get to the sign up function that anybody can call, it gets more complicated because we have to figure out stake allocation. So here, this is the sign up function. Again, somebody can pass in a list of stakeholders, stakes, and a name. And again, we're going to return an affiliate contract address. This time we do a little bit more validation to make sure that the number of stakeholders corresponds to the number of stakes. Again, we deploy an affiliate contract, but now we have to compute the parameters for the initialization function of that affiliate contract. So here, we are going to create a new stakeholders list that is separate from the one that was passed in as a parameter. It is an in-memory list of addresses. If we didn't declare this to be in-memory, it would become a storage variable that would be much more expensive to use and would get used, it would stick around forever. So this is a new list of addresses that is one address longer than the list that was passed in. That's because OpenRelay is going into this list of stakeholders. And then we make a list of shares that is the same length as the list of stakeholders. We set stakeholder 0 to be the beneficiary, which is OpenRelay. And we set the shares for stakeholder 0 to be equal to the beneficiary stake that is tracked on the contract. Then we iterate over the list of stakeholders, make sure that the number of stakes for that stakeholder is greater than 0. Because if they have said that any particular stakeholder has a stake of 0, it doesn't make any sense for that stakeholder to be here, and we should reject this whole transaction. Then we add up all of the stakes that this person has passed in. We're using safe math to do that, to make sure that the total number of stakes cannot exceed a 256-bit integer. After we've looped through here, we make sure that the total number of stakes is greater than 0. That basically assures us that, well, given that our stakeholders' length is greater than 0 and each individual stake had to be greater than 0, it would be nigh impossible to get here with stakes total being equal to 0, but again, get a belt and suspenders sort of thing. So then we iterate over our list of stakeholders, and in our new list of stakeholders, so this is the one that we're keeping track of in memory, we track the stakeholders that was passed in as an argument, and we set their shares equal to the total sender stake multiplied by this particular user's stake divided by the total stake. So I mentioned earlier that the sender stake is going to be 8,000 and the beneficiary stake is going to be 2,000. This means that all of the all of the affiliate stakes will add up to 8,000 no matter what they passed into this function. If they passed in that there is one person and they get 100 stakes, this is going to turn that into 8,000 stakes. If they passed in 2 people and each of them got 1,000,000 stakes, that's going to turn that into 4,000 stakes apiece. Anyway, that's the math that's going on there. We require that the initialization function succeeds. So this is going to initialize the target affiliate contract. We keep track of the affiliate in our affiliate registry, and we emit an event so that anybody who cares can see that we've just registered a new affiliate. Finally, we have a couple of general registry functions. So we can see, is somebody affiliated? It returns true if they are. That means that we have a non-empty string corresponding to this particular user. And we can also return the affiliate name. And it just occurred to me, and I should probably fix this before we deploy to mainnet. I think we're potentially allowing people to register with affiliate names as empty strings, which would mess both of these up. I should probably check at the registrations phase that the name cannot be empty. So now we get into the create proxy implementation function. And ignore the header on this slide. I seem to have messed that up. But basically, when you call the create proxy implementation function and pass in a target address, we launch immediately into some assembly code that will set up a proxy contract that is a mere 60 bytes worth of code. So the affiliate contract that we have takes up only 60 bytes. I think that's really neat. The 0x40 means we're allocating 60 bytes of memory. That's hexadecimal for 60. I know it looks like 40, but it's not. Then we write the target address so that this is going to be a 32-byte address, even though addresses are functionally 20 bytes. When we are writing to memory, we have to write 32 bytes at a time. So we start at byte 11, and we write out 43 bytes. Sorry, from byte 11 through 43, we write out 32 bytes of the target address. That include the first 12 bytes of that is going to be empty. So then, starting basically at byte -9, we write out this string of bytes. So this first 9 bytes worth of data get truncated off the beginning, and they don't go into that 60-byte array. Then we write the rest of this string going from byte 0 through byte 11. No, through byte 23. And then down here, after the address, from byte 43 through 60, we write this stuff, and then all these zeros go past the end of that 60-byte array. And then we create a contract using that contract code that we've just constructed, giving us a contract that is a grand total of 60 bytes and will successfully proxy our target address. If the code in the proxy contract ends up being 0 after we've deployed, then we're going to revert the transaction, and that is the deployment of our contract. For anybody wondering what that's doing, these are basically the opcodes that correspond to this seemingly random junk that we just wrote into that 60 bytes. I don't fully understand everything that this is doing. This is from a GitHub gist that a lot of people, including the founder of Ethereum, have contributed to, basically to play code golf and get the smallest possible proxy contract. The net result of this, so you can see down here that at line 22, we have a push 20 bytes opcode that will then immediately be followed by the target address that was encoded in up here when we generated the code. So essentially, the target address for the proxy is going to be hard-coded into the bytecode that we're deploying for the contract. So basically, our proxy contracts are 60 bytes total. The contract that we are targeting is currently 2,945 bytes, which means it is 525,240 units of gas cheaper to deploy our proxy contract than it would be to deploy a full affiliate contract for each user. If you figure that the network often requires you to pay 20 gigaway per unit of gas and $500 ether, that's about $5 savings for deploying a proxy contract instead of a full-blown affiliate contract. As I noted a minute ago, the target address is hard-coded into the bytecode of the proxy as we generated the bytecode in the contract. The proxy contract will be invoked as if it were the target contract. So you don't have to think about the fact that you're interacting with a proxy. You really just treat it as though it were the target contract, and then the bytecode, basically it executes the fallback function of the proxy contract, which does a delegate call back to the original contract to call whatever code you were trying to execute. But even though all of the affiliate contracts will share the same contract code, each one will have separate storage and addresses, which means that they can have separate stakeholders, they can have separate addresses, which means they have separate tokens. And so there won't be crosstalk between the different proxy contracts. It's basically as though we had deployed a separate affiliate contract for each one, but we saved $5 in gas for every one that we deployed. Any questions about the proxy contracts or the affiliate system or the affiliate factory?
Yep, I have one.
What's that?
Two. The first one is a basic one. If a vulnerability was discovered in the affiliate contracts that store payments, what could be done to update and fix them?
Okay, so for security reasons, we are not allowing any changes to the affiliate contracts themselves. The proxy contracts are hard-coded to a point to a specific address. However, we're not really thinking of these affiliate contracts as something that has to be a permanent fixture. So we would generally encourage affiliates, you've got this affiliate contract hard-coded into your DApp, perhaps, but it shouldn't be any more complicated than deploying a new version of your DApp to change the affiliate contract address to point somewhere else. If you're writing a contract that has something to do with your affiliate contract address, then you should make the affiliate contract address something that you could change in the event that you needed to point to a new one. So if there were a vulnerability, hopefully people would be able to disperse the tokens that are currently in their contracts the way that they're supposed to, and then we can issue new affiliate contracts. And yes, that means a new affiliate address, which is unfortunate, but generally speaking, we're trying to keep these contracts as simple as possible and allowing for internal upgrades to these contracts adds a significant vector of possible attacks that would complicate the contracts and increase the possibility of an attack by trying to make the contracts upgradable. So yeah, basically the answer is if we find a significant vulnerability, then we're probably deploying new affiliate contracts for any existing affiliates.
Okay. Next one is this all V2 0xv2 ready?
This has basically no dependencies on 0xv1 or 0xv2. The only so basically this proxy system or this affiliate system could be used for any situation where a contract is going to pay out to one address and then you want to distribute that to more people. So in the case of 0x, and this is true for both 0xv1 and 0xv2, orders have a fee recipient on them. So that fee recipient is going to be the affiliate contract address. The 0x exchange contract, again, whether we're talking about V1 or V2, will pay out to the affiliate address, and then somebody can call the payout function and distribute the ZRX tokens accordingly. In the event that we have come up with a new way to, say, pay takers, as we were talking about earlier, that comes up as a result of 0xv2, we might end up paying in tokens other than ZRX. We might pay in Ether. We might pay in ZRX. We might pay in Biggin. We might pay, who knows what we might end up paying in. But so long as it's an ERC20 token, this contract can already deal with it. So I think it's reasonably robust. It would not deal, for example, with ERC721 tokens, but I'm not sure how you do that. I'm not sure what it would mean to split ERC721 contracts, between, or sorry, ERC721 tokens among multiple people. If there's ever a need for that, that might be a case where we end up upgrading the proxy contracts or the affiliate contracts. But yeah, as it stands, there is nothing in here that ties it to 0xv1 or v2. And practically speaking, it could be used for a bunch of different purposes.
Okay. Lastly, this is a more idiotic question. Can the stakes be set to a negative number? I was trying to read the code as you're going over it. And
so, these are unsigned integers. Unsigned means they don't have the negative sign. So no.
Neat.
Yeah. Basically, they can't be negative. They could feasibly be so large that they overflowed, but we have checks in place for that. The one other thing that I want to point out, and this is pertinent to anybody who remembers the second parity multisig contract hack. So Parity used a similar method of deploying proxy contracts instead of complex multisig wallet contracts for people who wanted to deploy multisig wallets. And they got bitten very hard by that because they forgot to initialize the target of their proxies. and then somebody initialized it and became the owner of their base affiliate contract. And then to make matters worse, that base affiliate contract had a kill method that allowed that person who took ownership of the contract to cause the contract to self-destruct, which removed its code from the blockchain, which made all of the proxies that were pointing to it point nowhere, which meant all of the funds that were locked up in any of those proxy contracts were unusable. In this case, we don't have any mechanism for an affiliate contract to self-destruct. So even if we forget to initialize our base contract, it won't make a huge difference because there's no way to call self-destruct on the contract. So once this contract is deployed, it should be there in perpetuity, and there should never be any reason that it disappears. Any other questions? All right. So next time, we will be looking at the affiliate sign-up DApp and the affiliate monitoring microservice. So this would be the HTML and JavaScript of the application people will use to sign up for our affiliate program, and the microservice that watches for affiliate deployed events and writes those out to Redis so that we can know when an order comes in that this is a valid user. So but by the time we're done with that, we should have covered most of the broad concepts that OpenRelay deals with, dealing with smart contracts, dealing with front-end dApps, and dealing with microservices. And then we can move on and start going into more depth with some of the specific concepts. Unless anybody has any questions, that's all I've got.
Cool, man.
All right, thank you.